And next, we've got cloud intelligence, AIOps, infusing AI into cloud computing. The vision of large-scale, centrally managed computing and storage systems has been around for decades. In fact, Jim Gray envisaged a planetary-scale computer that could be managed by one person. In fact, even before that, Isaac Asimov dreamt up a similar system in the short story, The Last Question. Yet the technology we now know as cloud computing didn't really take off until about 15 years ago. There's been a massive migration of workloads to the cloud, and during which time the cloud has evolved and grown exponentially. But we're still a long way away from that dream of a self-organizing, self-managing system with a single person. The cloud and its underlying platforms must meet high standards for quality, including reliability, performance, efficiency, security, and sustainability. Even small changes in speed or energy consumption impact the people in the organizations around the world. Our next session features Qingwei Lin, a senior principal research manager at Microsoft Research Asia, who's going to talk about how cloud intelligence and AIOps are improving service, customer experience, and productivity of developers, and how AI and machine learning technologies can help design, build, and operate large, complex cloud platforms and services effectively and efficiently, with a lot less human intervention. So, over to you, Qingwei.
This is Qingwei Lin from Microsoft Research Asia. My topic today is on cloud intelligence, AIOps, infusing AI into cloud computing. This is the outline for today's talk. I will give an overview to introduce what is cloud intelligence, AIOps. Then I will talk about the cloud intelligence work at Microsoft. For the technology deep dive, in terms of the AIOps common research problems, detection, diagnosis, optimization, and prediction. I have one example project for each of them. At the end of the talk, I will also discuss some challenges and opportunities in the AIOps research area. We can see a clear trend for the future cloud. It will be much larger scale, and at the same time, stricter privacy and security are required, like sovereign cloud and air-gapped cloud. This requires full automation of cloud operation with little human intervention. In the meanwhile, the cloud would become more complex, which requires a global view when we would like to make optimal decisions. Also, higher cloud quality and higher reliability will always be a critically important demand. To prevent bad things to happen, we need to predict faults and embrace preventive strategies. All of these points us to an important direction for the future cloud: intelligence. Cloud intelligence is required to effectively and efficiently design, build, and operate complex cloud systems at scale. For the future intelligent cloud, we can see a clear paradigm shift. For example, we can envision that for the future cloud, we can learn from the rich cloud running data. So no matter how the system evolves, it can easily adapt to the new environments. For conventional cloud, the operations of the cloud heavily depends on the human efforts. We can envision that the future cloud should be autonomous with little human intervention. Also, in the future, it's required to be holistic and make optimal decisions with global view of the whole system. Reactive to outage is usually too late, as it already brings severe impacts to the cloud users. In the future, it should be preventive, which means that we can predict the upcoming outages and take proactive actions to prevent bad things to actually happen. So, what's cloud intelligence, AIOps? Cloud intelligence is to innovate the AI and machine learning technologies to effectively and efficiently design, build, and operate complex cloud systems at scale. It contains three key pillars: AI for systems, AI for customers, and AI for DevOps. In AI for systems, The goal is to design and build high-quality service with better reliability, performance, and capacity efficiency. In AI for customers, the key point is to improve customer satisfaction with AI technologies to provide better user experience. And AI for DevOps, the goal is to achieve high productivity with intelligent tooling. The scenario covers topics around each of the three key pillars of cloud intelligence. For system and infrastructure, the scenarios are all around the service health modeling, like anomaly detection, health prediction, and also auto-healing and auto-recovery. In DevOps, the focus is for development and operations. So the topics are around the programming and intelligence in CI/CD, which means continuous integration and continuous delivery, auto-diagnosis, and smart mitigation actions. The last one, customer intelligence, is all around the customer satisfaction. Scenarios like predicting customer experience, proactive customer engagements, and intelligent customer support. Among all these different scenarios, we abstract 4 major common research problems across multiple different scenarios: detection, diagnosis, prediction, and optimization. Each problem has its own challenges, like noisy data and labeling issues in the research problem of detection. While in diagnosis, the root cause can be very diverse, and there are highly complex service dependencies. In optimization, the huge problem space and complex constraints brings up big challenges on conducting global optimization. And in prediction, we will encounter the fast system evolution and unpredictable behaviors. Next, I will give an overview of some cloud intelligence work at Microsoft. Along with our partners in both product teams and research labs, we have been working on these aspects of AIOps, advancing state-of-the-art research, making real product impacts, and building AIOps community. I will quickly go through each of them. On the research front, we start the research on AIOps about 10 years ago. And recent years, we delivered some AIOps keynotes at top-tier conference and also other lectures and tech sharings. Since AIOps is an interdisciplinary research area, we publish papers at top conferences in multiple communities, including system, software, and AI, together with some awards like Best Paper Awards and Distinguished Contribution Award from the research community and the company. Here I list some of our publications in recent years. In cloud intelligence, AIOps area, including detection, diagnosis, prediction, and optimization. You can see that we have multiple papers in 3 major research areas. One is the system research area, like the OSDI, Unix ATC, and SDI. Another area is the AI research, like AAI, IJK, KDD. And the last one is software engineering, like ICSE, FSE. With the close collaboration with multiple Microsoft products, we have achieved some successful results in AIOps. For example, in detection, Gandalf self-deployments has been successfully applied in Microsoft Azure, capturing over 100 bad deployments. The precision was over 90%, and the record was nearly 100%, which means that we didn't miss any high-impact incident. In diagnosis, Log3C helps to successfully diagnose about 76% of the incidents of Microsoft Service X, and it has been applied and benefits to multiple Microsoft products. In prediction, NAYA performs prediction and actively chooses the most effective mitigation actions to prevent future failures. NAYA has achieved 26% improvements on the interruption rate reduction compared to previous strategies. In optimization, PPS has successfully served customer requests with 93% hit rate, and it significantly reduced the VM pre-provisioning time. In terms of community building, inside Microsoft, AIOps is a company-wide initiative from day one, with active participation from different organizations, including many important Microsoft products. The community organizes many AIOps events, like driving the annual report, white papers, special events, and newsletters to benefit the whole company. There are also AIOps activities for academia and industry. For example, blog series, tech articles, and AIOps workshop at top-tier AI, software, and system conferences. Next, I will introduce the 4 research areas. In each area, I will use one example project to illustrate how AIOps benefits the cloud systems. First, detection. Detection technologies are widely used in many scenarios across the whole stack of the cloud systems. For example, in compute, it can help to automatically detect the anomalies in time series, conduct safe deployments, or detect issues with logs. In storage, it can detect faults in hard drive or database, or low latency in disk I/O. Similar for networking, it helps to detect anomalies for network traffic, query latency, or network outages. Next, I will use safe deployment as one example to talk about AIOps detection technologies. We all know that unsafe deployments, even one small bug, may cause disasters in service availability. There are already many shocking news about how users are affected by a service down due to a very small bug in the deployment. So, deployment management is extremely critical, since the bad deployments may cause disasters in cloud systems. As a result, in Azure, the deployment process is an incremental way with several stages. In each stage, heavy domain knowledge is needed to manually validate the deployment quality based on various metrics from sensors, measures, logs, and events, and then decide whether this deployment can go to the next stage. However, as the complexity increases, this measure is labor-intensive and time-consuming. More importantly, it's error-prone. With safe deployment, our approach is as follows. We first perform the anomaly detection on various signals. Then, we conduct auto-assessment for the deployment based on the anomaly detection results to identify whether any anomaly is caused by the deployment. In the end, the system will automatically determine if this deployment can go to the next stage according to the assessment results in multiple dimensions. The goal is to create an end-to-end deployment solution, which increases the deployment safety and reduces the deployment time and human efforts. In short, it needs to be automatic, precise, and timely. However, There are multiple challenges. The first challenge is the diverse abnormal behaviors among the large number of metrics. Their patterns are very different. Another challenge is the labeling issue. We all know that it's hard to get enough number of the quality labels to do the training for machine learning models. To address the challenges, we first propose an anomaly detection method with active learning and transfer learning. We call it ATAD. In ATAD, we learn the knowledge from the open labeled datasets in transfer learning. As such, the required amount of the labeling data in our target domain is significantly reduced. Then we recommend a small number of samples to domain experts for labeling. In the active learning, so as to ensure model quality and fast convergence. Our evaluation results shows that we can achieve very good results with less than 0.1% human labels. This slide shows the results. So far, we have prevented hundreds of bad deployments with high precision and recall, and no severe regressions are missed. Some top-tier conference papers are published to summarize the technology or the system. Next, I will talk about the diagnosis part. Diagnosis is a very common demand for a wide range of scenarios in the whole stack of the cloud systems. For example, in compute, diagnosis is very popular in service downtime troubleshooting, log-based root causing, and performance issue diagnosis. In storage, it can help with database issue localization, I/O latency troubleshooting, and database issue root causing. Similar for networking, for its outage diagnosis, incident linking, or reasoning on dependency graph. Next, I will use log intelligence, as an example to introduce the AIOps diagnosis technology. Nowadays, log plays a critical role in cloud operations. Diverse types of logs are widely collected and stored. Log data is known as the most frequently used data for incident detection and diagnosis. Where we see huge amount of logs are stored, visited, and processed every day. However, the effective use of these logs is still far from satisfaction, especially for its effective use in the detection and diagnosis. We see pain points and how logic helps in detection and diagnosis. But that does not mean that simply adding intelligent algorithms into detection and diagnosis can solve the problem. The trouble exists from the beginning when log is generated. The quality of generated logs is not guaranteed at all, as it all depends on the habit of developers. Moreover, logs are processed improperly and insufficiently. Only with whole lifecycle governance and enhancement, good quality of log data can be obtained. The AI method can then realize their value. In order to boost the log intelligence, we proposed and designed a suite of solutions. Specifically, during the logging stage, we target to guarantee the logging quality with logging assistance. Then in the next log processing phase, we focus on how to convert unstructured logs to structured format to enable the downstream log analysis task. In the final stage, more systematic and comprehensive approaches are devised, serving all the intelligent detection and diagnosis process. The first stage is logging. In practice, engineers always complain that they cannot find useful logs in the overwhelming log data. So our goal is to improve the log data coverage for detection and diagnosis, but with fewer logs. Logging assistance includes two parts. One is word-to-log, which suggests suitable log contents, such as log level, static message, and variables. Another one is to recommend the right logging positions in the source code, which is called where-to-log. After logging, the next step focuses on how to process raw log from unstructured logs into structured format. Log is well known by its free text form. However, log is far different from commonly used natural language. It's machine language. It typically consists of header, template, and parameters. We expect to distinguish these three parts and organize them in a structured format to serve detection and diagnosis, as shown in the below table. For intelligent analysis, to accelerate the log diagnosis process, we designed a contrast-based diagnosis solution. It innovates machine learning measures to summarize consistent failure pattern from those failed components, and then identify which log or log paths are representative for the failure pattern, but rarely emerge in the normal components. Here are the evaluation results of our design components. From these results, we can see that our solutions outperform other state-of-the-art approaches. Also, it has been used in real production and have significantly improved the diagnosis efficiency. The third area is optimizations for cloud. Optimization is also a very widely used scenario in the modern cloud. For example, in compute, it helps with the optimal allocation and the scheduling for containers to optimize the workload missing and for intelligent power management. In storage, it helps with optimal defragmentation strategy, database management, and smart storage failover strategy. Same for network, for its dynamic load balancing, routing control, and topology optimization. I will use intelligent container allocation as an example to talk about the cloud optimization research. As we know, today, many top companies run most of their service in containers. Here is an abstract view of task organization. Within a cluster, a service consists of a set of containers, and containers are scheduled to run on machines. A quick note is that the sum of maximal container resource usages may exceed the machine capacity. In the proposed work, we leverage the trans-constraint optimization framework for container right-sizing and bin packing. This slide shows the motivation of trans-constraints in cloud. First, the QoS in cloud is defined as a form of the trans because unexpected events such as the hardware errors, software bug, and other outages happen from time to time. So the marginal cost is too expensive to ensure a deterministic 100% solution. In the container world, if the node has enough resource available, it is possible for a container to use more resource than it has requested. In this case, satisfaction probability alpha is proposed. To solve the above problem, we face two challenges in reality. The first one is the intractability of transconstraints. Here, we propose to use the independency and the Gaussian approximation to address this challenge. And the second challenge is that the objective is not well defined for a cluster with non-empty machines, which introduce new complexity. In order to handle such issues with non-empty machines, we propose a new metric named the UCAC as objective. UCAC means used capacity at confidence alpha. With UCAC, now we can differentiate which machine is better, considering multiple dimensions. From these results, we can see that our solutions perform much better than other state-of-the-art approaches. Please also refer to these papers to learn more about our optimization technologies in AIOps. The last research problem, prediction. Prediction technologies are important for many scenarios in the cloud stack. In compute, it helps to predict the service outages, cloud capacity, or to drive predictive workload scheduling. In short, in storage, hard disk failure prediction is widely adopted. It can also forecast the database faults or helps with storage planning. For network, it can forecast the network traffic, conduct routing management, and forecast the network capacity. In prediction, I will use proactive design as an example to talk about the prediction technologies. Traditionally, a classical control system would take the current status as input, and the corresponding decision-making are justified by a couple of rules from domain experts. However, such a reactive approach reacts to the past rather than anticipate the future. This is not enough for a mission-critical system. This slide shows the overview of the proactive design. In addition to the decision-making module, we incorporate the decision prediction module in the proactive design. As such, the system can learn continually by interacting with a dynamic environment and tell developer some information about the future. By leveraging this future information and early observations, developers can conduct proactive actions to minimize negative impacts or maximize resource utilization in the cloud. Proactive design is becoming a core engine for a wide range of application scenarios in cloud systems. It opens up new opportunities for a lot of proactive actions. For example, in capacity efficiency, it can trigger the emergency recovery in a proactive way so as to avoid the capacity crisis. In reliability, for example, we can forecast some big outages beforehand with symptoms from the current state and similar behaviors from the historical data. In this way, we can take some proactive actions to prevent or mitigate. similar for performance issues. For example, we can conduct early evictions for low priority VMs to avoid performance issue disasters. In Azure, Naya is a continuous probabilistic online solution for minimizing the customer impacts of hardware failures. Naya works in 4 layers. In addition to the prediction layer, the decision layer takes predicted results and past observations to choose an optimal actions in action layer. The resulting impacts are evaluated and feed back to the decision layer. To improve the robustness of Naya, we add a new safeguard at different layers. For example, it only allows relevant composite actions to avoid illogical scenarios in the action layer. Moreover, we have an override logic if other more severe issues are detected with an offline monitor. By leveraging Naya, the hardware-induced interruptions has been significantly reduced. Similar to Naya, Nanya is designed for smart database fault mitigation. In Nanya, we leverage a new RL model to enable end-to-end failure mitigation to directly output the final mitigation actions. We leverage the cascaded reinforcement learning for the cost-aware failure mitigation. In addition to answer the what to take, the proposed RL-based approach could also give a justification on when to take, thereby minimizing the cost of mitigation actions. Another example, the pre-provisioning service, short as PPS. In Azure, the VM provisioning time directly impacts user experience. The goal of PPS is to shorten the VM pre-provisioning time by pre-provisioning VMs under pool size constraints before real customer requests comes in. So we need to predict the VM demand for each VM type and then pre-create the VMs in the pool. If the request match the pre-provisioning VMs, they can use these VMs directly without any provisioning time. With PPS, the VM provisioning time has been significantly reduced in production. Here are the results of our designed components. From these results, we can see that our solutions perform much better than other state-of-the-art approaches, and they bring real benefits in real production. For example, with Naya, we can see 26% improvement on interruption rate reduction over previous strategies, and also 93% hit rate for customers provisioning requests by PPS. In the last couple of slides, I will share some challenges and opportunities in this research area. Here is the AIOps research roadmap. We can see that towards the AIOps research direction, in the future, AIOps will become more autonomous, proactive, comprehensive, and manageable. Currently, it's mainly AI assist, and later on, more components will become automatic, while in the end, it will become fully autonomous and automatic. In existing scenarios, it's mostly reactive after issues already happen. In the future, it will be more predictive and even preventive before bad things happen. It will also evolve from partial service to the whole cloud stack and to across different types of cloud systems. However, we still see a lot of challenges in front of us. In building AIOps models, it's a big challenge on how to obtain high-quality data, especially labels, how to deal with the fast evolution of complex cloud, and how to make the model generalized for a wide range of scenarios. It's also challenging on how to land AIOps solutions in production. For example, how to reduce the risk of AI errors, how to support debuggability of AIOps solutions, how to build trust with engineers, and to enable quick iterations. There are also some non-technical challenges. For example, to attract AIOps talents, to improve organizational effectiveness, and to set the right mindset for AIOps. But at the same time, there are plenty of research opportunities on AIOps models. For example, on data quality, how to control the quality of telemetry data, how to build robust machine learning models with limited quality data, and how to deal with heterogeneous data sources. As an ever-changing system, how to manage its dynamic nature, how to learn the dynamic dependency, and how to perform robust prediction. These all bring a lot of research opportunities. On the decision-making model, how to handle the prediction uncertainty, build the explainability, and transform the decision as a learning process. There are also a great number of opportunities on AIOps solutions. On infrastructure, a platform to integrate diverse AI models is needed, and the built-in support for training and inference is required. Resource optimization at every scale is another opportunity here. For generalization, we need scalable management systems, automatic customization, and also flexible strategy for heterogeneous environments. As for developers, we can see the opportunities in the AI-powered tools for productivity and also to rethink on the reliability and accountability with AI. As a summary, cloud intelligence is to innovate AI and machine learning technologies to design, build, and operate the complex cloud systems at scale. We abstract 4 common research problems among diverse AIOps scenarios: detection, diagnosis, optimization, and prediction. Thank you, and please feel free to contact me for any questions.